So what I want to do is, I know I'm not going to get to the acid-base section. I'll just do that part on your own. But we should be able to get through all the fluids and electrolytes. But I want to spend another, it'll go to the full time, and then if you could just stay for another 5 minutes, I want to do some inventory about what's going to happen in the next few weeks. So it's nothing to take notes on, but at least because it's going to pile up, and I just want to give you some suggestions about how to go about taking on the next few weeks till it's up to spring break. So we'll do that. All right, so let's talk about fluids electrolyte balance, and I'll show you how to put things together here, applying this stuff. Some basic stuff from A&P, just quick review stuff. What's in our body fluids, right? Our water is going to be our solvent. Remember, there's if you think of a pitcher of lemonade, right? The water itself is the solvent. The crystals that it's in, you know, that's crystal light, that kind of stuff. The crystals is the solutes. And then when you mix it all together, it's called a solution, okay? So our body, the universal solvent that's in our body at least, is going to be water. And that moves from one place to another depending on the osmotic gradients, where there's a higher concentration, moves to a lower concentration of water molecules. So the solutes that we have is basically things with charges and things without charges. So the electrolytes is the things with charge, things with salts, acid, base. Some proteins have a charge to it. Sodium chloride, those kinds of things. And then we also have non-electrolytes that will act as solutes, but there isn't a charge on it. This is going to be like your sugars, lipids, creatinine, urea when we get into those. Okay. And electrolytes seem to have a greater osmotic power than non-electrolytes. I'll show you what I mean by that. So when we look at the cell, we have this, we have cations and anions, right? A cation is anything with a positive charge. Think of a happy cat, right? A positive cat. And then we got anions that have a negative charge. So the most abundant cation in the cells is going to be potassium. The most abundant anion inside the cell is going to be phosphate. Now that does not mean that there's only potassium found, there's only potassium found only inside the cell. There is potassium outside the cell too. It's just that there's more inside, okay? When we're dealing with the extracellular fluid, the most abundant cation outside is going to be sodium, and the most abundant anion is going to be chloride, okay? So if there's more, let me just so you can put this stuff together. If there is more sodium outside the cell than inside the cell, okay? If the sodium gates open, does that mean the sodium is going to go flush inside, or is it going to rush outside? If there is 100 students outside this room, and there's 2 students inside the room, when those doors open, do the students want to go into the room or out of the room? Yeah, see? So once you start visualizing that, you'll understand. So it goes from a higher concentration to a lower concentration. Okay? And that's important. That should have been, explained to you and rehashed in a number of different ways in A&P 1 and 2, especially with the action potential, okay, and diffusion. All right, so we'll go more about that later on. So you don't have to memorize this. This kind of just shows you where these electrolytes are, the most abundant electrolytes in our bodies, and where are they actually located, whether inside the cell or outside. I kind of put it there just to be complete for you guys. Okay? Concentrations of the solutes. The concentration, when we put things in brackets like this, that means concentration of, in this case, the intercellular fluid. The concentration of the intercellular fluid must equal the concentration of the extracellular fluid. Otherwise, there's going to be differences that the body has to adjust to. And that's what this is all about. Because if it doesn't adjust, then we have disease processes going on. So they both have to be equal in concentrations of one another. And this is just some terminologies to put together. Won't test you on this, but if you see the words in your book and in your future classes, milliosmolarities. So basically when we have milliosmoles, there's 300 milliosmolarities in 1 liter per liter. That's telling you the concentration, Okay? We have milliequivalents that we also see, and really the main thing that we want to see, that we see often, is the percent sodium. The 0.9% sodium chloride. That's saying that there's 0.9% sodium chloride inside the cell and there's 0.9% sodium chloride outside the cell. If there's going to be a difference in there, then we're going to talk about where the water is going to shift. And that's what this major thing that we're going to be talking about with this fluid shift going on. So important principles of fluids and electrolytes. These are just kind of bullets just to remember from A and P Part 2. Homeostatic mechanisms respond to changes in the extracellular fluid, not changes in the intracellular fluid, by principles and properties that were explained to you before. There are no receptors that are directly going to monitor total fluid or electrolyte balance, but it does this indirectly through plasma volume and osmotic concentration. In other words, if there's a higher concentration of water inside the cell than outside the cell, then that's just gonna, there's no receptor. Water just will move to an area from a high concentration of water molecules to a lower concentration. It doesn't need to have gates open. There are certain things called aquaporins, but for the most part, we're gonna see just simple diffusion of water molecules from a high concentration to a lower concentration. And we'll go further into that. Okay? Cells cannot move water molecules by active transport. It's simple diffusion. When you have simple diffusion of water molecules, meaning moving from a high concentration of water molecules to a low concentration, that's simple diffusion, but it has a special name if we're dealing with water molecules. It's called osmosis. Something you probably wish that the book can do with your head, right? Just osmosis going through into your brain. But that's what it is. It's going to go from a high concentration to a low concentration. But when we're dealing with just water molecules, it has the special name of osmosis. Okay? And water follows solutes. You're going to hear that quite often, what I'm going to refer to. It's my little mnemonic to help you. Where does water go? Water is going to go where there's a higher concentration of salt or solutes. And we'll show you that. Okay? All right, so osmosis is the number of particles per liter of the solution, not what the particles are, okay? So it doesn't matter. When we see that there's 2 proteins on one side and 2 sodium on the other side, that's equal. It doesn't need to be 1 sodium here and 1 sodium over there. We're looking at the particles, okay? Water will follow salt, or water will follow solute. If there's more particles on one side, water will go to that side. Doesn't matter what the particles are, okay? So, this is where I'm saying that electrolytes have more of an osmotic drawing, oncotic pressure than the non-electrolytes. For instance, if you put sodium chloride in water, it will split up into 2 things. But if you put glucose that doesn't have a charge to it into the water, it only breaks up, well, it doesn't even break up, it just stays the 1. So therefore, you could have 1 water molecule going here and 1 going over here. So it has more of a drawing of the water because these things with electrolytes, then they have charge, they draw the water more there than these. Don't get me wrong, water does go where there's just glucose. It's just if you compare the 2, this has more of a drawing thing because they can break up into 2 things. Okay? So, which way will the water go? So if you have a cell, let's do a little interactive thing here. If you have a cell over here, and here's, I don't know, let's say these are sodium ions that are inside here, and then you have sodium on the outside. You're putting this cell into what type of solution when you compare it to itself? Are you saying that this is a hypotonic solution, a hypertonic solution, or an isotonic solution? Is it going into a more dilute thing or a more concentrated? Dilute. It's more concentrated inside. Outside, there's only 4 things here. 4 ions of sodium. Here there's, I don't know, let's say there's 15 molecules. So therefore, inside is more concentrated.
I thought there was less water.
I'm talking about the solutes.
Oh, okay.
right? So if you have more concentration of sodium inside than outside, then which way does the water want to go? Water follows solutes. Water is going to go where there's a more concentration of solutes. Now, one other thing, just keep this in mind. When I say hypotonic, it's a dilute situation. If I say a hypertonic, it's a concentrated solution. Think of the lemonade. Let's go back to the lemonade. You have a pitcher of lemonade. If I put crystals in there and a ton of water, is that going to be dilute or is that going to be concentrated? Dilute. So if it's dilute solution, we call it hypotonic. If we put a lot of crystals in there and a few drops of water, and you taste it, is it going to be really bitter or is it going to be dilute? Bitter. It's going to be very concentrated. And when it's very concentrated, we say that the solution is hypertonic. Okay? So let me ask you this. Is this just the cell, is that, when you compare it to the outside, is this hypertonic or hypotonic? Hyper, because it's more concentrated. Is this, the outside, is that more, well, is that hypertonic or hypotonic? Hypo, because it's more dilute. Does that make sense? Where is there more solute concentration? Inside or outside? Inside. Water is going to go where there's a higher concentration of solutes. So we put this cell into a hypotonic solution. Does the water want to go into the cell or out of the cell? Into the cell, right? Because it goes where there's more solutes. The water will go into the cell, and we say that the extracellular fluid is hypotonic. It's more dilute than inside the cell itself. Okay? All right, let's look at this situation. Obviously, it's the opposite, but let's go through the motions. Okay? Inside the cell, there's only 4 ions there. Outside the cell, there's many more. Outside the cell, is that hypertonic when you compare it to the inside, or hypo? Hypertonic. Inside the cell is hypo. Inside the cell is more dilute or more concentrated? Dilute. Is the outside more concentrated or more dilute? Concentrated. So, water follows solute. Water will follow where there's more concentration of solutes. In this case, does the water want to leave the cell or does it want to enter the cell? Leave the cell, because it's going to where it's more concentrated. It wants to get it so that the concentration is equal on both sides. If that happens, what happens to the cell? Does it shrink or does it burst? Shrink. Okay? So we say that in this case, the extracellular fluid is a hypertonic solution. The idea of which way it goes, understand it. Don't memorize it. Understand it, because we're going to need to apply this stuff, because you guys, you're going to a nursing program, you're going to need to know how to apply IV fluids and what that does to the body. All right, so it's going to be heavy now. We're going to apply stuff. But I'm going to show you. You don't have to memorize it. You just have to understand the concept. This is showing the same thing. Again, more concentrated inside than outside. Where water is going to go in, and then the cell will get bigger. So you're putting the cell into a hypotonic solution. Over here, you're putting the cell in a hypertonic solution. And when that happens, water goes where there's more concentration of solute, and the water leaves the cell, leaving a shrunken cell. We call that crenation. Okay? And in this case, where it's equal on both sides, well, the water isn't going to go either way, so the cell stays the same size. That's isotonic. Okay? All right, so do you understand that concept? Now, let's start applying it to real-world stuff. Let's see if we can start getting into, let's say, NCLEX type of questions, applying it. We're not going to be talking about a beaker and a red cell, all right? Let's go into what we're going to be dealing with. So here's a red blood cell, or any cell, but let's call it a red blood cell. And like I told you, inside the cell has sodium chloride. It's 0.9%. They did all the calculations. How they did that, I don't know. There's people that don't do research, or they do research and they usually don't have social lives, and they figured that out. Okay? That's what they did. So it's 0.9%. We don't have to figure that out. It's already done. So it's 0.9% sodium chloride on the inside. Normally, we should have 0.9% on the outside. But we have 3% sodium chloride on the outside. So again, I ask you, is outside the cell more concentrated or more dilute? More concentrated. Is outside the cell more, or is outside the cell hypertonic or hypotonic? Hyper. Is there more solutes outside the cell or inside the cell? Outside. So in a case like this, if you put IV fluids and you put not 0.9% in the bloodstream, which is this area here, but you put 3% sodium chloride in there, a higher concentration, does the water want to leave the cell or does it want to enter the cell? Leave the cell. Because it's going to go where there's a higher concentration. If that happens, then what happens to the cell? It shrinks. We call that crenation, that the cell crenated. Okay? And when that happens, then inside the cell, the functions and all the transcription translation doesn't work properly. You get sick that way. The enzymes can't be made and so forth. Okay? So keep in mind, it's not just the red blood cells, it's also the cells that surround the blood cells, like your liver and things like that. So everything. All right, so let's do this case. Again, you got a red blood cell, 0.9% sodium chloride inside the cell, but now we're going to give less than half of the normal saline, which is sodium chloride. Okay? Now the question is, if you put that in someone's blood, is that a hypotonic solution compared to the red blood cell or a hypertonic solution? Hypo, because it's more dilute on the outside. So does that mean it's more concentrated inside or outside? Inside. Water follows solute. Which way does the water want to go? Into the cell or out of the cell? Into the cell. Okay? And if that happens, what happens to the cell?
Grows.
Yeah, it grows. And in some cases, it grows too much and it bursts. We call that lysis. The cells burst. Okay? So the concept makes sense? Okay? And in an isotonic solution, which hopefully most of the cases that you're working in a hospital, you're going to be putting in 0.9% sodium chloride into the person's bloodstream. So the extracellular fluid is going to be equal as the red blood cells inside. What happens to the fluid there? Does it go into the cell or out of the cell? Neither, right? That's what we want. Okay? Neither way. And that's what we call an isotonic solution. That's why we give 0.9%. Certain cases, and we'll go through it, but there's certain cases that we do need to put in a higher concentration or a lower concentration. I'll show you a couple of situations in a moment. So let's go a little bit further. Let's give you numbers that might appear on your NCLEX or your other exams. Instead of 0.9%, they're using milliosmolarity. Don't let it scare you. You've got to compare the two. if the cell has 300 milliosmolarity, but in your blood it's 310 milliosmolarity, is it more concentrated in your bloodstream or inside the cells? Bloodstream. Is this hypertonic compared to this, or is this hypotonic? Hyper. So where is there more solutes? In here? I mean in the bloodstream or out? In the bloodstream. So where does the fluid want to go? Goes into, well, okay, where does the fluid want to go? Into the bloodstream or out of the bloodstream? Into the bloodstream. Does that make sense? Until it, follows solutes, okay? Now, let me also explain to you a little bit about diabetes. I'm not going to go into the details about diabetes. We'll get into that when we get to endocrinology. But in people who have uncontrolled diabetes, their sugar levels, their glucose goes skyrocket up in the bloodstream. Okay? Same thing we've been talking about, but I'll show you how we're applying this stuff. If you increase glucose in the blood, that means we're putting more solutes in the blood. Does that make sense so far? Is that going to draw water into the solutes, or into where the solutes are, or away? Into. That drawing power that we have is what I talked about before, osmotic or oncotic pressure. It's a drawing force, a pulling force. So if you have more glucose in the bloodstream, it's going to draw fluid from your cells and bring it into the bloodstream to try and dilute it. Right? Does that make sense? Okay? So osmotic pressure in the bloodstream is greater than the hydrostatic pressure in the bloodstream. So it's bringing in more fluid that way. If you bring in more fluid into the blood vessel, what does that do to blood volume? Does it increase or decrease? If you're bringing more fluid from the cells into the bloodstream, it increases blood volume. If you increase blood volume, what does that do to blood pressure? Increase it. Are you understanding the mechanism that people who have diabetes, it's no surprise that they'll end up having high blood pressure? You see the pathophysiology we're talking about. Instead of just memorizing, diabetes or increased risk for high blood pressure, sure. When you're taking pathophysiology, we need to know the steps of that. And then hopefully you don't have to do much memorization. It just makes common sense. Why does it do that? Okay? So water is pulled from the intracellular fluid to the extracellular fluid. You also get cellular dehydration. Does that make sense? The water gets pulled from these cells over here, so these cells are getting dehydrated. It won't function well. Okay? And it causes an increase of blood pressure.